In our last segment, we learned how to fit a set of data points y sub I, for a set of parameters b by minimizing the chi-square, and that gave a best fitting set of parameters b0. We also learned how to understand what the uncertainty is in those parameters as a posterior distribution of the actual value of the parameters b, and it came out to be this multivariate normal Gaussian distribution with covariance matrix sigma sub b, and since we're being Bayesian still, we could carry through the posterior probability of the parameters b if we want to do that. Now, we also commented last time that we might not be interested in all the parameters. Some of the components in this vector b might be properties of the instrumentation and not, for example, properties of the underlying reality of nature that we're trying to measure. And in this case, we want to do something to get rid of those uninteresting parameters and leave just the interesting ones to study. And there are two possible things we might want to do. We might want to marginalize or condition on the uninteresting parameters. These are two different things, and I'm going to explain them now. So marginalize. This is what you usually want to do. This means that you want to ignore the values of the uninteresting parameters, and as the word marginalize implies, you want to just integrate over them. How do you do that? Well, we have our chi-square function, and we learned last time that its second partial derivative matrix with respect to the individual parameters b is called the Hessian matrix. And we learned this relationship that if you take a half the Hessian matrix and then takes its matrix inverse, you get the covariance matrix of the parameters. And what you do to get rid of uninteresting parameters in the covariance matrix, if you're going to marginalize, is you just cross out the rows and columns of the covariance matrix, sigma sub b, that you're not interested in, and you take a submatrix of the interesting rows of columns of the new sigma b. And there, that's it. You've marginalized. That's kind of amazing, and you might be wondering, what is the origin of this fact? By the way, a special case, if you're interested in only one variable at a time, would be that you cross off all the other rows and columns. You're left with just a single diagonal component, and that's the variance of the parameters one at a time. We commented at the end of the last segment on that prescription. Well, it turns out that we've already proved the hard part of this theorem in a previous segment. We proved, if you'll recall, that the sigma parameter that occurs here in the multivariate normal distribution is also the covariance of draws from that distribution. We had to do a whole Cholesky decomposition to get that result. But once we know that result, then this crossing out of rows is and columns is just immediate, because covariances are just pairwise expectations. They're the expectation of the product of one variable times another variable, and they simply don't depend on whether there's a third or fourth or fifth variable around that we're considering not interesting. So in the covariance matrix, just take the submatrix of interesting rows and columns, of interesting parameters, and that is the covariance of the interesting parameters. Conditioning is different. Conditioning is pretty rare. When you condition, you want to fix the parameter values for certain of the parameters at specified known values. So why would you ever want to do that? Well, you might possibly want to do it if you have parameters in your experiment that you're going to determine much more accurately with a different experiment, or they're parameters that you can look up in a handbook more accurately than you can measure them, and you're going to want to then fix those parameters to these externally known values and learn what you can about the other interesting parameters in your fit. And the way you condition is kind of interesting because it's kind of the mirror image of this. Here we used the covariance matrix sigma b. In conditioning, down here, we simply take the Hessian matrix, or half the Hessian matrix, before we take the matrix in inverse, and we cross out the uninteresting values in the inverse covariance matrix. And then, if we want the covariance matrix, we take the inverse of the reduced matrix that's left. So it's an issue of, do you cross out the uninteresting variables in the covariance matrix before you take the inverse, as here, or after you take the inverse, as here? Now, because conditioning is rare, I'm not going to tell you the whole story, because there's another part of the story that if you condition uninteresting parameters to any values that are different from the ones you've measured, from the values b0, then your means also shift. In other words, b0 itself of the other variables will also shift. And I'll leave it as an exercise for the reader to calculate that shift, or look up in Wikipedia the article Multivariate Normal Distribution and look at the section on conditioned distributions. Here's an example in just 2 dimensions that might make this all a little bit clearer. Suppose that the Hessian matrix, after multiplying by a half, came out to be these numbers: 50s on the diagonal and minus 49s. Of course, it's a symmetric matrix, so there's really just one number here, minus 49 on the off diagonal. I've cooked that up just for this example. So that would be the inverse of the covariance matrix of these 2 parameters in the 2-dimensional B. And if I take that matrix inverse, I can get what the covariance matrix is, and it turns out to be numerically about 0.505 on the diagonals and about 495 on the off diagonals. Now, in 2 dimensions, the probability distribution of the parameters has contours that are very elongated ellipses like this. So for purposes of this discussion, let's imagine that the probability is all concentrated inside this. Maybe this is the 2 sigma error bar of the probability distribution. But in any case, it's an ellipse that shows the shape of the concentration of the distribution. So let's see what the difference between marginalizing and conditioning is. And this is going to be in the case where we're interested in the value in the parameter y, and the nuisance parameter, the uninteresting parameter, is x. So marginalizing means that we take the probability density here inside this ellipse and we project it onto the y-axis. And so you can see that the uncertainty in y is kind of from here to here. The fact that we're not interested in x doesn't reduce the uncertainty in y, and this distance, square root of 0.505, came from crossing out the uninteresting parameters in the covariance matrix, leaving only this number 0.505, and then taking its square root, which is the value shown here. In conditioning, on the other hand, we might say, suppose that we know the value of x from some other experiment, and we know that it's exactly 0. In that case, we cross out the uninteresting parameters here in this matrix, and then we're left with 50, and we view that as a matrix. We take the inverse matrix, that's 1 over 50, and that's a variance, and we take the square root of that to get a standard deviation, and that's shown here. That's this small interval here. By the way, you might have noticed that we're always putting a subscript b on our covariance matrices here to show you that they're the covariance of the fitted parameters. And there's a reason that we're doing that, to avoid some confusion. Now, I know whenever I say don't confuse xyz, that's immediately going to confuse you about xyz, so I'm going to have to take that risk here. We started off with a data set, and that data set had errors. And those errors can be viewed as the covariance matrix of the data. Now, when we started off with this form for chi-squared, that was the form where the measurement errors were all independent. And so the covariance matrix of the measurements was a diagonal matrix with basically sigma I squareds down along the diagonal. But all of this formalism would go through if the data, the original data, had correlated errors, and their covariance matrix would be called sigma without the subscript b. And then back to the original definition of chi-squared, instead of being this one over here, it would be this matrix definition over here involving the covariance matrix of the data. So this covariance matrix of the data, which usually we take to be diagonal, has nothing to do with the sigma sub b up here that we've been talking about, which is the covariance matrix of the fitted parameters after you've gone through the whole nonlinear fit mechanism, minimizing chi-squared to get those parameters. Let's see how this works out in our example with 5 parameters. You'll recall that this was our model, and we're going to be interested in just B3 and B5, or eventually in just their product. So I did that exercise of crossing out the rows and columns of the 3 uninteresting parameters, B1, B2, and B4. And then I had MATLAB compute the matrix inverse and gave these results. And I can plot these results as error ellipses. We learned how to do that when we talked about Cholesky decomposition in a previous segment. And so here, in the two-dimensional plane of the interesting parameters, are what we get as a visual representation of these covariance matrices. The covariance matrix when we condition the uninteresting parameters, and the covariance matrix when we marginalize the uninteresting parameters. And the bigger one is always going to be the marginalized one. We saw that on the previous slide in our one-dimensional example, and now we're seeing it in a two-dimensional example. So conditioned errors are always smaller, but generally that's not what you want anyway, because generally you don't have any other way to measure accurately the conditioned parameters, and what you want to do is marginalize. So let's talk about some general properties of maximum likelihood estimation estimates. Frequentists love MLE estimates, and not just in the case of a normal error model as we've been doing up to now. MLE estimates have provably wonderful properties asymptotically, and asymptotically means as the amount of data becomes very large. And here are some general properties of all MLE estimates asymptotically in the size of the data set. Consistency. The MLE estimate of a parameter will converge to the true value of that parameter. Equivariance, so-called. If we want to know a function of the parameters, if we want to estimate that, for example, B3 times B5 would be a function of the parameters, the estimate of the function of the parameters becomes asymptotically the same as the function of the estimate of the parameters. That's a nice property to have. And MLE estimates are all asymptotically normal. The best one of all, MLE estimates can be proved to be asymptotically efficient, that is to say, optimal. And what this means is that if these first 3 properties are all desirable properties, and you think of all possible estimators of the parameters with these properties, then the MLE estimator will have the smallest variance of any of those. Frequentists have a different name for what we've been calling the Hessian matrix of the chi-squared. They view it as the second partial derivative of the log of the probability of the data given the parameters. This is, of course, the likelihood of the data. And this is called the Fisher information matrix, and its relationship to the inverse of the covariance matrix of the parameters is as shown here. The only difference is the Fisher information matrix technically has an expectation brackets here. It's an expectation over the population. Not to worry. Now, I've given you a sort of a pro-frequentist view in the first part of this slide, but I want to say that as Bayesians, we're a little bit skeptical of all of these things. Not of the mathematics, which is very, very pretty, but we tend to be skeptical of any results that are asymptotic because we live in a non-asymptotic world. In our example, we had 20 data points, and with exactly 20 data points, none of these properties hold in any particularly useful way. We live in a non-asymptotic world. On the other hand, we tolerate MLE estimates because MLE estimates are almost Bayesian. The only reason they're not Bayesian is that we assumed a uniform prior probability, and we could have put back in that prior probability and tracked it through the formalism, and then we'd be even happier. I want to finish up with a small digression so that you know what a confidence interval or a confidence region is. This is essentially an alternative description of what we've been calling covariances. The idea in one dimension is pretty obvious. When we say what a variance is, we say what a standard deviation is here, or, for example, what about 2 standard deviations plus or minus is on this curve. Now, we could quote the same region of uncertainty by just saying from here to here is a confidence interval that contains 95% of the area of the curve. So instead of quoting a covariance, we would quote a confidence interval, and we always have to say which confidence interval it is. For example, the 95% confidence interval. But how does this generalize to more than one dimension? Well, in more than one dimension, you have to give a confidence region. You have to give a region in your higher dimensional space that contains 95%, or whatever number you're going to state, of the total probability. And if you think about it, you'll see there's no unique region because you can sort of move the regions around a little bit as long as you just keep including 95% of the probability. So all of those would be, in principle, equally good 95% confidence regions. However, there's a convention in use. The convention is to use contours of the probability density as the shapes that you look for which one of those contours contains 95% of the probability. And as we saw, the probability density on the parameters is e to the minus a half delta chi squared, or e to the minus a half chi squared. And so these are also contours of how much chi squared differs from its value at the maximum likelihood value at the center of these ellipses. And of course, the use of these contours means that we're going to be giving the maximally compact confidence regions. So the remaining question that we have to answer is which delta chi square contour contains which amount of probability, so that we could, for example, locate the 95% one. And I'm going to breeze through a little geometrical argument to give you the answer to that. This is probably something that you'll want to go away and think about. So which delta chi squared contour in new dimensions contains some percentile probability? Well, the delta chi squared contours come from a covariance matrix, sigma sub b. And that covariance matrix we could visualize as an ellipsoid in the number of dimensions equal to the number of parameters, for example 5 in our favorite example. And we could imagine rotating that covariance matrix and rescaling it, squashing down the probability in some directions to make it a sphere. If I really wrote this out in equations, this would be another one of those Cholesky decomposition things with a vector y related to a vector x by a Cholesky factor L. Well, once we've done that, then each dimension in this sphere, or hypersphere, is an independent normal distribution. They're independent because it's spherical, and they're normal because any affine scaling or rotation of normal distributions is also normal. And now in this spherical space, you can see that the contours are just labeled by the square of the radius because it's a sphere. And the distance out to any radius is given by the sum of new independent t-squared values. In other words, delta chi-squared in this space is distributed by our favorite chi-square distribution. Chi-square is a function of nu. And once we figure that out by a geometrical argument, then it's just a question of finding what are the percentile area points under the chi-square distribution curves for various percentiles. And here's a table where I've worked it all out for you. So our one-dimensional example was that two standard deviations. Now, delta chi-squared is like a variance, so it's like the square of standard deviations. So a delta chi-squared of 4 from the minimum, in other words, you go away from the minimum until the value of chi-square increases by 4, and in one dimension that will contain about 95% of the probability. But if we're interested in two parameters, then we have to use this column, or this curve, and go out to this 95 percentile point. And you'll see the delta chi-squared then is a little bit over 6. And it increases slowly with the number of dimensions, that is to say, with the number of interesting parameters whose joint probability distribution you're interested in. The reason I'm spending so much time on this is that people frequently learn facts that are just wrong. A typical fact that people learn is that a delta chi-squared of 1 is the 68% confidence level. And we see that that's true only in one dimension. It's the value right up here. And in fact, the 68% confidence level of a confidence region in two or more dimensions has delta chi-squareds that are greater than 1, as shown here in the table.